visualizations for biomolecules, for proteins in this case. And so nowadays we're dealing with large multidimensional and dynamic data sets. For example, arising from complex molecular dynamic simulations with hundreds of thousands of time steps and millions of atoms. So, and I think it's important to mention here that the structure of these molecules is often important for the function. So the structure itself, so the spatial arrangement of the atoms and the spatial arrangements of the whole molecules with respect to each other. So molecular visualization, as we've also heard in the morning, often uses stereoscopic rendering so that users can easily see these or perceive these spatial relations in stereoscopic views. So many available tools like VMD or PyMol support power walls, caves, or VR head-mounted displays. But nowadays, augmented reality is on the rise. I guess no one in the room will object to this statement, hopefully. And here I want to mention that I want to focus on augmented reality using see-through head-mounted displays. So not the video-based augmented reality that's also possible with smartphones or cameras. So I'm talking about devices like the HoloLens, like Darkreef smart glasses, or the upcoming Meta 2 or other devices here. There are, of course, many applications for augmented reality. Popular examples are, I would say, guidance systems for manufacturing, repair, maintenance, stuff like that, where users have this see-through visors and get virtual clues what to do next. But of course, there's also a whole new field of research called Immersive Analytics. So to put it simple, this uses immersive technologies, so virtual or augmented reality, together with natural user interfaces, so for example, physical navigation, voice recognition, and stuff like that, for visual analytics, so for data analysis, for visual exploration of complex data sets. And so our goal, our long-term vision, so to say, would be to build a collaborative augmented reality environment to analyze molecular data sets, so molecular structures in a natural way. And for this case, untethered systems like the HoloLens are of course perfect, because if you have multiple users running around, you don't want to be tethered with a cable to a PC. So users interfere with each other's cables and can trip and stuff like that. So we want to have an untethered solution, ideally, like the HoloLens. So to further flesh out this vision a little bit, so we think that a collaborative visual analytics or immersive analytics environment for molecular data would be a natural way to show 3D data, so to have a 3D display for three-dimensional data. So you can just walk around your molecules together with your peers or your students. You can have this physical navigation that I just mentioned. You can have gesture recognition, for example. You can have physical props like 3D printed molecules that interact with the virtual molecules. You can have voice recognitions. But you can also still naturally communicate with your peers while analyzing the data, because you still see them through this see-through visor. So you're not completely immersed like in a VR system. You don't need to use avatars. You can still take notes or look at a conventional PC screen while working in the augmented reality environment. So that's all benefits that we think will become useful in the future. And of course, there's also the classroom scenario where students can, as I said, still take notes and see the teacher, instructor. The problem is, one problem that we see here is that augmented reality needs high frame rates to ensure user comfort. So Microsoft, in their performance guidelines for HoloLens, actually state that you should have 60 frames per second. And of course, you also want to have a high image quality because, if your molecules don't look natural, the immersion is also not that high. So you need to have high frame rates, and you want to have good-looking graphics, so to say. However, that's a problem because, as you might know, the HoloLens hardware is quite limited, the capabilities. You have a 1 gigahertz Intel Atom CPU. The SLAM is handled by a specific holographic processing unit, but the GPU specs are widely unknown. But they're, an Atom great GPU, so nothing too good. On the other hand, as I told you before, modern molecular visualization is quite demanding. There are many complex molecules. So in this work, the goal of this specific work was to evaluate the rendering capabilities of HoloLens. So this is kind of a feasibility study for the collaborative immersive analytics environment that we are planning to implement. And for this, we chose a baseline case, namely the space filling rendering that you can see here. So each atom is just displayed as a sphere. And this is, so to say, a ground truth rendering for many applications. So yeah, the space filling model is one of the simplest models that that are available for molecular data. So to test the performance, we implemented a small prototype. It's not based on Unity, like many people do, but instead we created a standalone universal Windows platform application written in C++ to get maximum performance and to know what the engine is doing, so to say. So it uses direct 3D11 for rendering. It can load real-world data sets from the protein data bank, so it can load protein data. And we implemented, and the video's not playing. Sorry about that. Yeah. So here you can see a small video capture of our system, just a space-filling rendering of a molecule of a small protein floating in space. And we actually implemented 6 different rendering modes for spheres to find out which one is the best, gives the best performance in HoloLens. So the first 3 rendering methods are, so to say, the classical computer graphics approach. So you have a sphere, which is discretized into triangles, like you would do in a computer game. And the first and obvious strategy is to upload this pre-tessellated sphere, this triangulated sphere once, and rendering using the instancing functionality of the graphics cards for each atom you have. So you can render the same sphere over and over, change the parameters so that the colors and the radii are correct, and this is efficient. On the other hand, the second rendering mode uses adaptive triangulation using the tessellation shaders. So the tessellation shaders, if you're not familiar with modern GPUs, allows you to generate triangles on the fly, on the GPU while rendering. So you just upload the center and the radius of a sphere, and all the triangles that build up the sphere are created in the shader. And on a desktop GPU, this is quite efficient, so you have less data to upload, and fast desktop GPUs can generate triangles quite efficiently. And the third rendering mode we implemented here for triangulated spheres is to actually also use this adaptive tessellation from the tessellation shader, but to render only the front-facing hemisphere. So you can see this here in the sketch. Since you won't see the backside at all, you don't need to generate triangles for this backside. So you have the same image quality, so the same number of visible triangles, but you just have a lower triangle count because you omit the backside. And this at the cost of just 1 barometrics multiplication to rotate the hemisphere so that it faces your camera directly. Now on modern GPUs, you can also do a different rendering, so without explicitly rendering triangles, but instead using what's called GPU-based raycasting. So you can see this in this sketch here, the general idea. So instead of tessellating the spheres into triangle, you just render a small, minimal geometry, a sprite, so to say, that covers the whole sphere. And then in the pixel shader, you compute your ray sphere intersections, and then you get a pixel-perfect image of your spheres without generating triangles that discretize the sphere. This is actually the fastest method on current desktop GPUs. So even though this is quite involved, because for each pixel you have to shoot a ray and compute this ray sphere intersections. But as I said, since you don't need to render all these triangles, it's a very, very good solution. And for this, we also implemented 3 versions. The first one also uses instancing. So here we have 2 triangles that cover the sphere. And we instance them, so we render the same two triangles for all the spheres, and then we can do the ray casting in the pixel shader. And the second option is we can also use the geometry shader. The geometry shader, similar to the tessellation shader, can also generate triangles on the fly on the GPU. So here we generate these two triangles on the GPU. And the last solution is using tessellation shader. So here in this case, we create a pentagon. So why a pentagon in this case and not two triangles? Well, as you can see here, there's in the pentagon case, there's less empty space in the corners. So here in these corner cases, you also have to execute those ray-sphere intersections. And so in this pentagon case, we wanted to reduce the number of unnecessary ray-sphere intersections that have to be computed. And yeah, as you can see here, we have this pixel-perfect image quality, so you don't see any polygon edges like you do in classical computer graphics. Okay, so these are the 6 rendering modes, 3 triangle renderings, and 3 different ways to render this GPU-based sphere ray casting. And what I should mention here is that we assumed from the beginning that sphere ray casting might not be a good fit for the HoloLens GPU, because Microsoft actually says you should reduce the number of pixel shader instructions. So yeah, they actually recommend that you don't use per pixel lighting, but rather per vertex lighting, since the GPU is so slow. So for the performance measurement, we choose 5 different data sets. So the smallest one just has 1,000 atoms, so it's a really small insulin fragment. And going up all the way to 50,000 atoms, which is a not really huge data set, but a fairly large protein. So this is the large subunit of a ribosome. And we had in-between data sets, so going in steps up to this 50,000 atoms. So these are the test data sets. And all these proteins for rendering was scaled to fit within a 0.5 meter box, so about 2 feet side length. The proteins are always the same size in space, just the atoms get smaller the larger the data set gets, it's scaled down. The testing protocol was as follows. So we automatically placed the protein in space and rotated it around the x and y axis at a distance of 2 meters and 1 meter. Because this numbers were chosen because we wanted to, or we thought this would be the typical viewing distance when a user walks around the virtual protein and looks at it. And we also had a fly-through from 2 meters away all the way through the proteins to 2 meters behind it. So if we now look at the numbers, so here you can see the measurements for the smallest data set of just 1,000 atoms. For the rotation case, so here are the numbers for the 2 meter and for the 1 meter case. And what's striking here is that only one method actually reaches the target of 60 frames per second. And this is the very, so to say, stupid sphere instancing. So no fancy shader tricks here, just regular triangle rendering, no adaptive tessellation. And this is actually the only case that reaches the Microsoft recommendation of 60 frames per second. The raycasting cases, so we have the geometry shader, the tessellation shader, and the instancing are about the same speed, or almost exactly the same speed. And also the tessellation spheres and hemispheres are about the same speed. So as you can see here, rendering only hemispheres is a little bit faster because we have less triangles. Sorry. But it doesn't make much of a difference. And it's way slower than using the instancing. Even though the number of triangles that are generated here by the adaptive tessellation is actually lower. So just using the tessellation shader is much more expensive. Now if we look at the number, if we come closer to the protein, we see that the frame rate drops considerably. So for the raycasting cases, this is to be expected. I mean, the closer we come to the protein, the more pixels are filled by spheres, and we have to do the raycasting. So this gets expensive, and yeah, we expected this drop in frame rate, and we can see that the frame rate is way too low to be called interactive. What we also encountered is that now at 1 meter distance, the triangulated sphere rendering is almost the same speed. So again, we see the full spheres using tessellation shaders are a bit slower, but using instancing and tessellate hemispheres is about the same speed. What you also encountered here is that 30 frames per second is kind of good enough for immersive rendering. So you see a little bit of jittering sometimes, but it's still okay. So from our experience, we'd say 30 frames per second is okay. It's not great, but it's good enough. I'll quickly show the number for the other data sets. So as you can see here, for the medium-sized data set, the instant sphere rendering is still almost good enough. But for the larger data sets, the rendering is just too slow. So there's just one more interesting thing here to notice. So for the very large data set, for the 50,000 atoms, the raycasting solution actually becomes faster. And we assume that this is because here we have so many triangles to render that the triangle rendering gets too expensive. So if we have very large data, raycasting would be faster. But then again, rendering speed is too low to be usable anyway. So, and what's also interesting is that we actually found that using per pixel lighting doesn't hurt the performance considerably. So in contrast to what Microsoft tells you, we switched from per pixel lighting to no lighting at all, and the frame rate was almost the same. So per pixel lighting doesn't hurt you that much. And this actually brings me already to my conclusion. So we implemented an initial prototype for augmented reality molecular visualization on HoloLens to evaluate the rendering speed. And we found that simple instancing is usually the best solution, except for very large data sets. So if you use a lot of shader instructions, that's going to hurt your performance considerably. So yeah, stick to the very basic rendering. But it's also worth to mention that HoloLens can only render small to medium-sized data sets interactively. For larger data sets, we will have to resort to level of detail renderings or simplified representations. So that's something that we are planning to do for future work, make it possible to render large data sets in reduced detail. We also want to add support for multiple users, as I told you in the motivation. And we want to extend the user interface, since right now we are using a voice command-based interface, which might not be ideal if you're collaboratively looking at the data set.